Okay, good morning. Uh, Getting everything set up here. Um, so just some brief review from last day because it was just on Tuesday, I guess. But just a tiny little bit of review. We talked about distributions and describing distributions, right? And specifically, we talked about the shape of a distribution. And so maybe I'll say shapes of distributions. And so what we said was, okay, one of the main shapes that we're going to have to deal with is the normal distribution. So a unimodal, so one peak, symmetric bell-shaped curve. Okay? And so here, if it's unimodal and symmetric, we call it a normal distribution. Sorry, I don't know. Everything's weird today, I think. Probably just me. Let's see here. So what was another shape that we could talk about? Oh, I should emphasize it a little bit more and maybe scoot this over here, there. What if we have something like this, right? We call that a skewed distribution. So now I'm focusing on the unimodal distributions, and we call this a skewed distribution. And this is skewed in the direction of the tail, which is heading left or in the negative direction. And so this would be skewed left versus the other direction, which would be skewed right. So we're going to focus on these unimodal distributions and whether they have a tail to the left or a tail to the right, it doesn't matter. We're going to lump those into, and we're going to call them non-normal distributions. So what we're going to talk about today is if we have a normal distribution, and we introduced it last day, but it was kind of towards the end, so that's why I want to kind of pick up there. But if, and maybe I'll use pink, why not? If the distribution is normal, the appropriate measures of center and spread are, oh, a participant had, I don't know what it said. I missed it. Sure, it's fine. So if the distribution is normal, okay, the appropriate measures of center and spread are the mean. Well, maybe I should say, I'll say center and spread. Yeah. Let's talk about if we have a normal distribution, right? Then our best measure of center is the mean. And for the spread, we talked about the variance, and then I feel like I had a brief moment to introduce the standard deviation, but what we're going to focus on in this course is the standard deviation. And so the standard deviation. I'm going to introduce it here because we'll start talking about it today. So it's not really review anymore, I guess, but for a non-normal distribution, the measure of center that we're going to use is called the median. And for our spread, we're going to use what's called the interquartile range. We're going to introduce those today. But just so we have a handle on that there are differences depending on the shape. Okay. So for the mean, we said that, okay, the sample mean is denoted by X bar. So typically just a generic X, and then anything with a bar over it just denotes that it's a sample mean, right? And so notice that it's from the sample, so it's called a statistic just in general, right? And so we can also talk about the population mean, which we denote by a mu. And so a Greek letter mu. Okay. And so this is a statistic, and this is a parameter. Right? Statistic is a measurement from the sample, whereas a parameter is a measurement from the population, right? And so notice these matching S's and P's. Okay. And so to introduce summation notation, we said, okay, well, if I asked you to calculate the average, right, then you would say, well, I would add up all my things and divide by however many I have. And so how we're going to denote that is the sum from I equals 1 to n of x subscript I over n. So we had that summation notation. And then we introduced, and maybe I'll pick up here, then we introduced the variance, which is on the next slide here. Okay, so this is from last day. Let me get my pointer here. And we quickly built up to this more sophisticated summation notation and just a more sophisticated formula in general, right? And so, and we broke this down and we said, okay, the variance, we're going to denote it by S squared. That's the sample variance. Okay. And so maybe I'll add it here. We said the variance was the statistic is S squared. So many colons, sorry. And the parameter is sigma squared. And you know what? I've got a different way that I want to do this, I think. I'm going to set it up as a table instead. So this is the variance. The statistic is S squared, and the parameter is sigma squared, right, for the population. But if you've calculated it, it's a sample statistic, right? So S squared. And then I feel like we didn't quite have time to get into the standard deviation, which is the square root of the variance. But the statistic for the standard deviation is a lowercase s, and the statistic for the parameter, or sorry, the notation for the parameter is sigma. Okay? Take the square root of s squared and you get s. Take the square root of sigma squared and you get sigma. We ignore the negative options, right? Because we can't have a negative spread, so that's fine. Okay. So then we spent some time breaking down each component of this formula, right? And so what I want to emphasize here is, to me, it's not important that you know how to calculate the variance by hand. That's not important to me because we have software to do that. But it is important to me that you are able to take a formula like this and break it down and know what to do if you had to, right? It's not something that I would make you do on a test. I'll make you do it on an assignment maybe. And so just knowing how to do it and how to get a formula like this and break it down, that's what I'm interested in. Okay. And so we spent quite a bit of time talking about this here. And then, yeah, briefly, I had a chance to talk about the standard deviation. But with that, I'll call this the end of the review. Kind of introduced some new things there, but that's okay. So just a couple of notes on why do we use the squared deviation to calculate the variance. First thing, and I feel like I mentioned it because I always do, is that it eliminates any negatives that you have. So you have these distances, so deviations from the mean, right? And the mean is the center, right? And so because we have a normal distribution, so the mean is at the center, so some values are below it and some values are above it, right? And so if values are below it, then the deviation is going to be negative. Now, if you added up all those deviations, you would end up at 0 because that's how the average works, okay? And so you don't want to do that. That's not very useful. And so to get rid of those negatives, that's why you square them, okay? And then another thing is when we square values, right, it makes the larger deviations, they're penalized in a heavier way. And so, for example, if the deviation is 1, right? So some observation is 1 unit away from the mean, right? Then 1 squared is 1, right? So it just stays 1. But what happens, right? I increase by 1, okay? Now my deviation is 2 away, but what happens when I square it? All of a sudden I'm at 4, so it amplifies, right? So it amplifies large deviations. Good. So we've already seen it, but the standard deviation is the square root of the variance. And so you need to find the variance before you can find the standard deviation, unless of course you're using Excel, which we are in the labs, right? Then you can just calculate the standard deviation, that's fine. But because there's a standard deviation command. But in general, if you're finding it by hand, then you would need to calculate the variance first and then take the square root. Okay. That's very. I wonder if she does. Okay, good. Might need to grab a tissue here soon. 'Tis the season. Okay, so I don't want to talk about that yet. Okay. So in our pseudo review, we said that, okay, fine. If we have a normal distribution, then we can use the mean as the center and we can use the standard deviation as the spread, right? So now if we have a non-normal distribution, so if we have a non-normal distribution, we use the median as the center. We use the median as the center. Okay. Now the median is the value that splits the data in half. Okay, so in order to do that, you're going to first need to sort your data, right? And so I guess it doesn't really matter if you go ascending or descending, but I would never do descending. That's weird. But so you sort your data, okay? from smallest to largest. And then for me, what I use is my my patent pending no, it's a joke, but my patent pending boop 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 method. Okay, so we're only going to be doing this for small data sets, and so it'll be kind of reasonable to be able to just do it on by hand. Of course, Excel has a median function, so it can calculate the median for you, a larger data set. But in general, for me, when I calculate the median, so our data set is 0, 1, 2, 3, 4. What you do, so first sort the data. Step 1, sort the data. And then step 2, boop, boop, boop. Boop, boop, boop. Your way in to the center to find the central value. Okay, so here, boop, boop. So I just put my fingers on the 2 outside values and then I boop, boop, boop my way in. Now this is a very small data set. And so here, where I land is on the 2. Okay. So if there are an even number of observations, okay, then when you boop, 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 you land on 2 values. Okay, and this is pretty nitpicky stuff, but just to make sure that you're able to get the right answer in the assignment, which is, you know, where marks are. So then the rule that you're going to follow is that if you land on 2 values simultaneously, then the median is considered to be here between the 2. Okay, so what you do, kind of confusingly, is to find the median, you take the average. That's weird, right? But you take the average of 2 and 3 in this case, and you end up at 2.5. And so here, 2.5 is the median. We can also call this the 50th percentile. Okay, and so a percentile in this case, or in any case, right? The 50th percentile says that 50% of the data is below this point. Okay. So, good. So it's not too bad as long as you remember to sort your data first. That's going to be the most important part, and then find the midpoint, right? Remembering that the median is the midpoint. Okay. And let me just scroll ahead here. Okay. And I want to add a page maybe because I've got a couple more things to say. The median is robust to outliers, right? So extreme values. So if we consider a data set like, so for example, if we've got 0, 1, 2, 3, just stealing the one from up above here, 4, 5, right? Then the median is going to be 1, 2, 3, 4 here, right? The median is 2.5. We just did that. If we had to find the average, no, I think I forgot my calculator. I did. And I don't tend to use my calculator. Or sorry, I don't tend to forget my calculator, but if I take the average of these, right? So then here, X bar is going to be 1 plus 2 plus 3 plus 4 plus 5 divided by 1, 2, 3, 4, 5, 6. Oh my gosh. Oh, my computer. Oh no. Oh, do I have to do that? Sorry, this computer is very annoying. Okay, I was gonna add 1 plus 2 plus 3 plus 4 plus 5 divided by 6. The mean is also 2.5. Okay. This is because it's symmetric, right? So then the mean is the median, if it's perfectly symmetric. But if we have, so now consider 0, 1, 2, 3, 4, 50. Right? It's not 5 anymore. Now it's 50. So now what happens to the mean or the median? Let's start there. Bing, bing, bing. The median is still 2.5. That's great. What happens to the mean? 1 plus 2 plus 3 plus 4 plus 50 divided by 6. All of a sudden, right? 1, 2, 3, 4, 5, 6. Yeah. X bar, oops. X bar, the mean, is now 10. Right? So what we'll see, or what we see here, is that the mean is pulled in the direction of the tail. Or outliers. And so for that reason, right, we say that the median is robust to outliers because it'll still hold steady in the center, right? And so it's not affected by those extreme values, right? Because now, right, this, right, would look like a very skewed distribution, right? If we visualize this, this would look something like this, right, with 50 out here. So that's just important. So to remember is that the mean is going to be pulled in the direction of the tail. And so whereas the median is going to hold steady, and that's why the median is a better measure of center if you have a non-normal distribution. Nice. And so for the spread, for non-normal distributions, we use what we call the interquartile range. Okay. We use the interquartile range, or the IQR, as the measure of spread. Okay, so what is it as the measure of spread? So the interquartile range, I'm going to introduce it here, and then we'll develop it more on the next slide. But the interquartile range is the distance between the quartiles, or the quarters, the quarter marks, is the distance between the quartiles, specifically the 25th percentile and the 75th percentile. Remembering percentiles, right, we have the 50th percentile is the median, meaning that 50% of the data is below it and 50% of the data is above it, just knowing how percentages work, right? And so the 25th percentile has 25%, percent of the data below it, right? Which implies that 75% is above it, but we're only talking about the data, the percentage of data below this point. And so now the 75th percentile has 75% of the data below it. Okay. So the 25th percentile is also called the first quartile, which we denote Q1. Okay. And Q1, I'm going to show you how to calculate it, but it's basically the median of the lower half, right, of the data. The 50th percentile we already introduced and know how to find is the median, and then the 75th percentile is the third quartile, which we're going to denote by Q3. Okay. Between Q1 and Q3 is the middle 50% of the data. And maybe I'll add that to here. No, it's on here, that's fine. Okay, so the range these data span is called the interquartile range. So the interquartile range is Q3 minus Q1. Okay, and so you have to find the third quartile, and then you have to find the first quartile or some version of that, and then subtract the two. Okay, so to find the quartiles, how about find the IQR of, let's say 7, 4, I'm just making up a data set here, 7, 4, 3, 8, 2, 9, 11, 15. All right. I've got how many data points? 1, 2, 3, 4, 5, 6, 7, 8. Okay, cool. So now, first thing we have to do, right? This doesn't look sorted to me, so I have to sort it. So step 1, sort. So then what I like to do is I just like to kind of indicate that I've used it. So I can check my work. 2, 3, 4, 7, I think. 8, 9, 11, and 15. 9, 11, 15. Just count them again just to make sure. 1, 2, 3, 4, 5, 6, 7, 8. Looks good. Make sure they're sorted. Looks good to me. Gonna add a page. So now, step 2, find the median. I'm going to copy this. Oops, because I can. It's kind of cheating, I think, but saves me some writing. Look at how weird that is. I needed lines. Okay, fine. I'm just gonna quickly write this out, but straight. 2, 3, 4, 7, 8, 9, 11, and 15. Too funny. There. Finding the median. We were on a board or whatever, then I would take my fingers and you try not to go cross-eyed too much, right? But boop, 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 boop. So the median here is 7 plus 8 divided by 2, which puts me at 7.5. Okay, so now the median is at that line. Okay, and so the rule is, and we just need to remember the rules, right? Is that this is the median. Okay, I haven't used either of these values as the median, so I'm going to show you an example where we do use it as the median, but we don't use either of these as the median, and so we can start, right? Because so here the median splits our data in half. Now what do you want to do? You want to split it into quarters. Well, that's going to be taking this data here and splitting it in half, right? And so now, step 3, find Q1. Got the space. You can just do it on the same one. It's fine. But so now I'm looking at this data here, and I want to find the midpoint, right? The first quartile, split it into quarters now. So you split it in half, and then you split that lower half in half. And so here, boop, boop, which means that Q1 is 3 plus 4 divided by 2, which is 3.5. I'll say step 4 over here, find Q3. Sometimes I do a subscript, sometimes I don't. Hopefully it's okay. So now I'm finding the midpoint of the upper half, right? And so now I want to use 8 to 9, 15 to 11, and I land on these. And so then Q3 is 9 plus 11 divided by 2, which I feel like might be 10. Okay. So here, one thing I want you to note is that this is because median is neither 7 nor 8. Right? Just as a quick example, now consider the same data set, but what I'm going to do is I'm going to remove these. And let's say we remove this 2, right? So now I have one fewer data point, but that's okay. So what can I do to find the median? So it's already sorted, that's fine. And so now boop, 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 boop. 8 is my median, right? I landed on that value. So the median is 8. Okay. And so here, what you want to keep in mind is that now we can't use this value in our quartiles, in finding our quartiles. We can't use this value in calculating the quartiles. Okay. And so what does that look like? Well, it means that I'm starting at 7, right? Because I can't use that 8. And so Q1 is equal to 4. And again, I'm not allowed to use this 8 because it's already being used as the median. And so now going from 9 to 11 and 15 to 11, I find that Q3 is equal to 11. So just a couple of rules to remember. In the end, Excel has a quartiles function and a median function and all kinds of good stuff. So it's not, super important, but like I said, when you're answering the assignments, the assignment questions and the test question, because you'll need to do it on the test, then this is the method that you have to use, okay? So that's why it's very important. Okay. We can build so often. we summarize these values using a 5-number summary. The 5-number summary is a numerical summary of the distance or the values that split the data into quarters. And so the 5 numbers are these, and I'll write them here. The minimum, Q1, the median, Q3, and the maximum. Okay, they have to be in this order. Must be in this order. Okay. And so in this, let's do this previous case here. Copy. Paste. I'll zip it up. Okay. In this case, the minimum and the maximum are easy because you've already sorted your data. So those you can find very quickly. The minimum is 3 and the maximum is 15. Because I'm talking about the one where I removed the 2. Just picked one. Q1 is 4, Q3 is 11, and the median was 8. So this 5-number summary, our brains don't do a great job of reading the 5-number summary and understanding the distribution of the data, which is the goal. Okay, and so that's kind of tricky, but what we can do, you know what? I'm gonna cave. I'll put it on a fresh page here. Whoop. There. That's cleaner, I think. Okay. And so now, right, this is hard to visualize. Okay. And so these distances between the quartiles, that's hard to visualize. And so for that reason, we introduce a visual summary, a visual 5-number summary called the box plot. Now it's on the next slide, but before we get there, I want to introduce one other key thing. Okay, and so what we can do here, from the 5-number summary, we can calculate the interquartile range, which is Q3 minus Q1. So in this case, the interquartile range is 11 minus 4, which is what? 7? Who knows? Let's see here. Just need to confirm. Yeah. Okay. So now what we're going to do is we use this distance to determine if a value is an outlier. Okay. And so in a data set, okay, in a data set, we use the 1.5 IQR rule to determine if there are any outliers. Okay. And so what the 1.5 IQR rule says is that, okay, from the lower bound, or the lower bound is going to be from Q1 you're allowed to go down as far as 1.5 times the interquartile range. 1.5 times the interquartile range. Okay. Any values smaller than the lower bound are considered outliers on the lower end. On the lower end. Okay, so I'll go to our summary here. From Q1, I'm allowed, so from 4, I'm allowed to move down 1.5 times the interquartile range. Okay, so in this case, in this example, what do we have? We have the lower bound is 4 times 1.5, or sorry, minus 1.5 times 7. 1.5 times 7, I get 10.5. 4 minus 10.5. I get negative 6.5. Okay. What that means is that if I go to my data set here, I can put this here, right? Negative 6.5. So now I can see I'm allowed to go as far as negative 6.5 before anything is considered an outlier. Okay, and so here, all the data on the lower end are wrapped up above negative 6.5, right? And so then I can say I don't have any outliers on the lower end. So what we can say is, since there are no data points less than negative 6.5, there are no outliers on the lower end. We still have to do the same thing on the upper end. So what we did was we took from Q1, we were allowed to go down a distance of 1.5 times the interquartile range. And that's just a set rule. You could have, there are other rules that you could use, but the most widely used rule is 1.5. Okay, so that's what we're going to use. And so by the same method, from Q3, I'm going to move up 1.5 times the interquartile range. But that changes our formula slightly, right? From subtraction, so moving down from the Q1, now I want to move up from Q3, which means I have to add. Okay? And so now the upper bound is Q3 plus 1.5 times the interquartile range, which in this case is Q3, which is 11. Okay. And then plus 10.5. So I get 11 plus 10.5. And maybe I should write it out. You're allowed to just skip like that if you want to. 1.5 times 7, since you already showed your work. But I'll do it properly here. So I get 21.5. So again, paste. I had a bound at negative 6.5. And now what I'm going to do is on this number line, I get 21.5. all the values are within these bounds, okay? And so there are no outliers, right? But this is how you would determine if there was an outlier. Since there are no data points above 21.5, there are no outliers on the upper end. Oh, good. So now what we can do is a box plot is a visual representation of the 5-number summary and the outlier calculations. A box plot is a visual summary, or maybe a visualization of the 5-number summary and the 1.5 IQR rule calculation for outliers. And the 1.5 IQR rule, oops, calculation for outliers. So now we're ready to see a box plot. Now a box plot looks like this. And so, of course, we've got a box in the middle. That makes sense, I think. And so let's focus on the box for just a little bit. Okay. At the very center, there's a line, and that is to denote the median. Right? Remember, it's a visualization of the 5-number summary. Okay, so we start with a line at the median. Okay? And it's possible that you can turn this box plot and change your axes to the x-axis, but usually for space-saving reasons, we do it this way. And so, and also it's nice to be able to read the axis like this. So those at the middle is the median. The values are increasing as you move up, making this value, I'm going to tell you it's a quartile. In fact, it's the first quartile. So this is Q1. Okay. So here, this line is Q1, making this line Q3. Okay. Good. So now we have this, the box is for the quartiles. Okay, so then you make a box here. And I'll draw the median pink. So now, just in terms of vocabulary, I guess, these are called whiskers. Oh, kind of glitched out there. These are called whiskers. Kind of cute. Right? And so sometimes a box plot is called a box and whisker plot. Okay. But notice how there are no values beyond this whisker. Okay, that's the equivalent of saying, okay, then this point is the minimum. Okay, and so in this case, this is the minimum. Okay? So the whiskers are drawn to the lower bound and the upper bounds. And then if there are values beyond that point, then we denote them with just dots or stars, depending on what software you're using, right? You're not going to draw these by hand, you're going to use software, but it's good to know the anatomy of a box plot, which I saw is the name of the next slide. But so here, this is the maximum. whereas this is the largest value within the upper bound. Yeah. So the whiskers extend to the minimum or the maximum, so extend to the largest data point within the data set that's within the upper and lower bounds. But if you have those values beyond the upper and lower bounds, then they're considered outliers, right? So what color can I use that I haven't used before? Uh-oh, I used up all my best colors. Too similar. Fine, red. That's weird. Ugh. These are all considered outliers. So the maximum is outside the upper bound, and so it's considered an outlier, but we still draw them, right? We just want some way to indicate that, hey, these are actually considered outliers by the 1.5 IQR rule. Okay. Nice. So here we could use a dot plot, which we talked about last day, but usually I would want to talk about the box plot instead. And so here, this is all that we said on the previous, or when we wrote in the textbook, they talk about the whiskers as the horizontal lines. Okay, yeah, so totally. So here, thank you. Yeah. I circled these things, but I shouldn't have. Should I have? These are the whiskers, but they get extended down. So I guess the T part is the whisker. Yeah. Nice. But it is this horizontal part. Good. Keeping me honest. Okay. So here they outline again what the 1.5 IQR rule is and does and how you use it. And so we'll just use it for a little bit of review because we only did the one kind of cheap example. Okay. And so whiskers of a box plot can extend up to 1.5 times the interquartile range away from the quartiles. And so what we said was, okay, the max upper whisker reach, or I call it the upper bound and the lower bound, doesn't matter, is Q3 plus 1.5 times the interquartile range, right? So you're moving from the quartiles out respectively. Okay. So here, the maximum lower whisker reach in this data set, which we don't have, was -5. Now I want you to look here and say, okay, well, so the whisker didn't go down to -5. It only is it's allowed to go to -5, but it doesn't. It goes to the data point. Okay? And so kind of nitpicky stuff, but an outlier is any observation that's beyond these upper and lower bounds. Outliers, we need to keep an eye on outliers just because extreme values are interesting, especially in statistics. We're usually concerned with those extreme values, but also to make sure that it's not a data collection error or something like that. So we've already talked about this, but right, how would sample statistics such as the mean and the median, the standard deviation and the interquartile range of household income be affected if the largest value is replaced with 10 million, right? And what if the smallest value is replaced with 10 million? So here what we're getting at is the median and the interquartile range right? The interquartile range is the distance between the quartiles. Well, the quartiles don't care about extreme values, right? We're looking at the distance between the distance between the middle 50% of the data, or the distance of the middle 50% of the data, right? And so it doesn't care about those outside values, whereas the mean and the standard deviation absolutely do. So here, if we just have a look at this table, right? If we have some original data, now I don't really care to know what it looks like, right? It looks like this. They've kind of shown a dot plot or a stacked dot plot. I would have preferred a histogram, I think, but that's okay. So then if we have the original data, then the median was 190 and the interquartile range was 200,000, but I'll ignore those units. The mean, X bar, is 245 and the standard deviation is 226. So now, if I'm going to move the largest to 10 million, what happens? Well, my median and the interquartile range stay the same. And then same, kind of similar, but there's a subtle change if I move the smallest to 10 million. So now I'm shifting my data over just a little bit, and that explains the smallest shift in the median. Whereas here, the mean is changing from 245 to 309 to 316. And same thing, the standard deviation just absolutely blows up when we alter the data. Okay. And so here, we've already talked about this, but the median and the interquartile range, they're more robust to skewness and outliers than the mean and the standard deviation. So that's why for skewed distributions, we should be using the median and the interquartile range. Okay. Whereas if you have a symmetric distribution, so not even a normal distribution, but any symmetric distribution, what you can use is the median the mean and the standard deviation for the center and spread. Okay. So now, if you want to talk about the typical household income for a student, would you be more interested in the mean or the median? And we said, okay, last day, anything that has to do with money is typically skewed to the right. Okay? And so here, right, typically money looks like this, generically. Okay. And so what we're going to find is that the median is going to hold steady, and it is an appropriate measure of center, right? Versus the mean is always going to be pulled in the direction of the tail. So the mean is pulled in the direction of the tail. So it might be somewhere out here. So just to visualize, so I'm not, I don't know, but, right. And so here, right, the mean is pulled in the direction of the tail. But that means that if the distribution is symmetric, then the mean is going to be very similar to the median. So notice it's got dot, 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 dot. And so for that reason, then you're allowed to use the mean because the mean has more tools associated with it. So then you absolutely could use the median all the time, right? But there are going to be benefits to using the mean instead. And so if it's symmetric, then you can use either. The problem is you'll always be able to calculate both, right? It's just a matter of knowing when it's appropriate to use the median versus the mean. Okay. So if the distribution is skewed or has extreme outliers, then we usually use the median. So if it's right skewed, right, imagine it's skewed to the right, right, then it would look like this, right? So then you've got your median, which is less than the mean, versus something like this. In that case, the mean is less than the median. Hmm. So now we're given a distribution, which is most likely true for the distribution of percentage of time actually spent taking notes in class versus on Facebook, Twitter, etc. I don't think those are the go-to ones anymore, but that's okay. Right, just kind of describing the shape here. It's skewed to the left, which tells me that, okay, the median would be somewhere around here, a relatively accurate measure of center, whereas the mean is pulled in the direction of the tail, so it might be somewhere here. Now, I draw these lines willy-nilly. I'm just trying to, maybe not willy-nilly, but it doesn't matter where you put them. It's just relative to each other. Where are they, right? And so the median would be with the bulk of the data, whereas the mean is going to be pulled in the direction of the tail. Okay? And so here, the mean is less than the median. Which is this one. Nice. We'll just talk briefly about extremely skewed data. So there are data out there that are extremely skewed, okay? And so what we can do is we can take what we call a log transformation, okay? This isn't something that I'm going to test you on. It's just in case you are doing your own analyses and you have something like this, you have a very skewed variable, then one of the tools that you can use is to take the log of the variable. Now, usually we use and maybe I should use a different color here. Log base E usually, or log base 10, and some sort of log. But there is an error on here, because here we've got the number of basketball games attended, and here we've got the number of basketball games attended, but that's not quite true. It's the log of the number of basketball games attended. And so here we've got this very, very skewed distribution. When we take the log of it, then we get this distribution that we can deal with, right, and kind of visualize. Now, interpretation is going to be very difficult, okay? I shouldn't say very difficult, it's just more difficult than just talking about the number of basketball games attended, right? Now we have to talk about the log of the number of basketball games attended, which you'd have to kind of untransform later. And again, there's a typo here. The log of the number of games. The log of 70 is 4.25, and I can't tell if they've used log base 10 or log base E. It actually doesn't matter as long as you're consistent, right? And so here, right, the results of the analysis might be difficult to interpret because the log of a measured variable is usually meaningless, right? If you say, oh, the log of this was 4.25, well, that doesn't mean anything to me, right? So then you'd have to untransform it. but it is a helpful tool and something to kind of remember if you're dealing with very skewed data, but not something that I would test you. Except maybe like a multiple choice question, I might say something like, how do you deal with extremely skewed data? Or yeah, multiple choice. Log transformation. What other variables would you expect to be extremely skewed? Sometimes, oh, uh-oh, my battery's running low. Oh my gosh, this thing's falling apart. Crazy. No wonder I never use this laptop. Let me see here. How low is it? No way of knowing. Weird. Oh well. Right. Usually money is very skewed. We've talked about that, right? And so that's one of the options. There's lots of skewed variables. So intensity maps are just kind of a fun visualization, and they're used all the time. And what are they? Well, sometimes they're called heat maps. Okay, so here I'll add or heat map. Heat maps were all the rage about 10 or so years ago, 10, 15 years ago. And so made some heat maps myself. Uh-oh. What happened? I don't know why it stopped my video, but that's okay. It's all falling apart. I'm gonna unplug this so I'm not stealing juice anymore. Okay. And so what's it doing? Well, it's assigning a different color to different levels of the data or the variable, right? And so here, change in population, the darkest blue has the highest increase and the darkest yellow has the highest decrease, right? Or most extreme decrease. Just kind of a fun example. Let's see here. I wish I could tell how much of my battery was left on here, but it's all full screen and okay. How about we'll end it here because I'll pick up on categorical data. Oh yeah, that's my iPad. It's I've got multiple things going on. And I worry that I was pulling juice from the laptop because I thought it was, well, it was fully charged. Just transferred it. That's okay. I didn't think we'd get this far anyways today, so that's great. So I think what we'll do is we'll end here and we'll pick up with categorical data. Oh my gosh, on Tuesday, I guess. And we'll also start chapter 3. So if you're reading ahead, we are going to get into 3.1. And so we'll do, so this is 2.2. So on Tuesday, oops, we'll do 2.2 and 3.1. Okay. So we'll stop there. I'll handle my scandal over here. And I hope you have a wonderful weekend. And I'll post an assignment for 2.1 so you can have some practice. All right. If you have any questions, let me know. Otherwise, I'll see you next week. And I'll stop this recording here.